Hello everyone, and welcome to your third lesson of your chemistry revision course. Hope you enjoyed the other two so far. So today we will be covering group 1 and group 7, their reactions, trends down there, the groups, and just some general things about them. So firstly though, we're going to start with a balancing equation, so one that we met actually back on the first day, so your iron one. Okay, so how are we going to balance this equation? Once again, let's start by counting up our different atoms. So iron, we have 2 ions on the left hand side, only 1 on the right. And then how many oxygens do we have? We have 3 on the left, actually no, we have 4 on the left. So because we have 3 and the extra on there. So how many do we have on our right? We have 2 on the right. So then what happens? So then if we count our carbons, we have 1 on the left and then 1 on the right. So we can see that we're going to need to balance our ions and our oxygens. So the iron, we can just put a 2 in front of it, and then we're going to get 2 ions, and that's been sorted. So to balance the oxygens, we've got 2 on this side. So we could try by multiplying the carbon dioxide by 2, but this is going to cause a significant different change on this side. So we're going to have to think about that side. So the best approach to do this one is to get an even number of oxygens on our left-hand side. So how can we do that? If we put a 3 in front of our carbon monoxide, how many oxygens are we going to get on our left-hand side? We're going to get 6. Okay, so how many oxygens would we need on the right-hand side? We'd also need 6. And we can see if we multiply carbon dioxide by 3, we're going to get to this number 6, to 6 oxygens. So then we put a 3 in front of our carbon dioxide. And now we're going to recount our atoms on the right-hand side, and on the left-hand side. So our oxygens have become 6. Our carbons have gone to 3. Our carbons on this side have also gone to 3. And our oxygens on this side have gone to 6. So therefore, it is a balanced equation. Hope everyone understands that. Okay, so now let's start our topic of the day, group 1 and group 7. So as we know, these ones are the group ones down here, and our group 7s are right here on the right hand side. So we know that from our staircase, this side's non-metals, that side's metals. So group 1s, they're all metals, and group 7, they're all non-metals. So what do the groups tell us? We know that what's in group 1 has 1 electron in its outer shell, and whatever's in group 7 has 7 electrons in its outer shell. So we're going to start off with our group 1. How do the group 1s react? So a few properties of group 1. Firstly, one thing to remember is that they are called the alkaline metals. That's like what they might refer to it in your exams, so be very well aware of the different names of it. So next, group 1 metals, they are very reactive. We're going to see why just in a bit. But also, you may have seen them in class, hopefully some of you have, but they are always stored in oil. And this is because they're so reactive that they're going to react with all the oxygen in the air. And another thing to remember is that the reactivity increases down the group. Okay, so properties. So these alkaline metals, group 1 metals, they have very low densities. So that means that they float on water. Okay, so water has a density of 1 gram per centimeter, -3 per centimeter cubed. And the alkaline metals, they have a density even below that, which is very, very light for metals. They're also really soft. Maybe some of you guys have seen this in school where your teachers cut them, and that's not very typical for a metal, is it? So soft metals is a very important trait of theirs. They're also very active because they only need to lose one electron. This is key to remember. Only need to lose one electron to get to that stable configuration. So as soon as they lose this one electron in their outer shell, they get to be happy because they have their stable configuration. They have the same configuration as a noble gas. So if we look at, if we take, say, sodium, for example, so sodium has 11 protons because the proton number is 11, so therefore it also has 11 electrons. So let's draw the electronic structure of sodium. So how many electrons does the lowest energy shell take? As we've seen yesterday, it's only 2 electrons. The next shell, how many does that one have in it? We know that it can take up to 8 electrons, and at 8 it is a full, happy, stable configuration. However, if we add 8 and 2, we only have 11 electrons now. And we know that sodium, it has, 8 plus 2 is 10. And we know that sodium actually has 11 electrons. So therefore, we can see that it's got this 1 electron in its outer shell. And once it loses it, we're going to form a stable structure with 8 electrons in its outer shell. Okay? And also, remember, it forms a positive ion. So this new structure, it has a plus charge, a positive charge. Okay. So it's very important to remember. Reactivity increases down the group. So what reactions do we see? So alkaline metals have low densities, very low densities. And yeah, the reaction with oxygen is oxidation. So reactions with water. Have you seen this at school before? Metals, they float on the water and start to fizz. So fizzing, we always know whenever something starts to fizz, it's to do with a gas. A gas is being released, okay? In this case, it is hydrogen gas. So once the sodium loses its 11 electrons, so once it forms an ion, it's just called a sodium ion. So it's just Na+. That's what the sodium forms. So metal floats on water and fizzes. The fizzing is due to a gas being released. So metal reacts with water to form H2. As we know, H2 is a gas, so that fits perfectly. So the fizzing is because hydrogen is produced. So this is your reaction of the alkaline metals with water. We can see here H2 is produced, which is the gas, and here is our hydroxides. So the alkaline metals are called that because they form this in water. And as we should know, hydroxides, they are alkalis. And alkalis have high pHs, pHs greater than 7. So 7 is neutral. Anything higher than 7 is an alkali. And this is what a reaction that you need to remember and be able to apply to. So any alkali metal with water goes to form its hydroxide and hydrogen. So let's do that for potassium, right? So we know that potassium and water is going to form what? Do people want to quickly write down some answers? People have any idea? Yeah, brilliant. Lots of correct answers. So we're going to form potassium hydroxide and hydrogen again. Once again, we're going to have to balance this equation slightly because, so how many potassiums do we have on the left-hand side? Let's do some more balancing. We have 1. How many hydrogens do we have on the left-hand side? We have 2. How many oxygens do we have? We have 1. Then we have 1 potassium, 3 hydrogens, and 1 oxygen. So the hydrogens need to be balanced. So if we put a 2 in front of this hydrogen, 2 in front of this one, we balance our hydrogens because now we have 4 on this side, 4 on this side. We've got 2 oxygens, and so we've got 2 oxygens from here, but we now have 2 potassiums on the right hand side, so therefore we need to add a 2 in front of the potassium here. Okay, brilliant. I can see lots of correct answers. So how do they react with oxygen? So they react with oxygen to form the metal oxide. So this is a metal oxide. So then if we say take potassium again as an example, how we're going to apply this. Do people want to give it a go? So potassium plus oxygen, what's it going to form? It's going to form potassium dioxide, sorry, potassium oxide. And once again, we need to balance it. So we're going to put 4 in front of here, 2 in front of here, just the same. So they follow exactly the same patterns. It's really good to know these equations because they quite commonly come up in your exams. Okay. So potassium. So you might have seen, so some of you may have seen sodium at school. How sodium reacts in water. If you put it in, it starts fizzing and it moves around the water, the beak of water. But no one will have done, actually some of you may have done an experiment with potassium. But if you haven't, we're going to watch a video of the reaction of potassium with water. So here, you can see your potassium is this metal block, and they're cutting it up.
It has a consistency of cream cheese. The potassium.
So could you see it's a very soft metal? So if
extremely soft. We can easily we expose the shiny metal surface underneath.
So once you cut it up, you see this shiny metal surface, as he said, and it's really soft because usually if you say took iron, you would never be able to cut it up like this. Okay.
The potassium is extremely soft. We can easily flatten out the potassium metal. It has a consistency of the metal conductor. Add a piece of potassium metal to water.
Now here is our reaction with water. Okay, this bit's the fun bit.
Potassium metal to water. We see that it reacts much more rapidly with the water than the sodium. As you go down the column, the ionization energy decreases and the metal reactivity. Okay,
hopefully you enjoyed that video. And you got to see how the potassium, it burns. So no, the potassium doesn't burn. So the potassium, it has a very fast reaction with the water, and the H2 ignites. And that's why you get that flame when you're on the water. Okay. Next one. Questions? So not all metals do this. It's just because group 1 metals are super reactive. That's why group 1 do it. So yeah, brilliant. The reactivity does increase as you go down the group. So when you reach, say, really low down the group, when you reach, where is it? When you reach, say, here, it's an explosive reaction with water. Like, it's not really done because it's so fast and so vigorous that it caused an explosion, which is interesting. There's some videos on that on YouTube, so if you're interested. Okay. So now we're going to move on to our group 7. If there is any questions on group 1. So group 2 is not more reactive than group 1. Group 2 is a lot less reactive. No questions. Okay, brilliant. So now let's move on to group 7 then. So group 7, you may have heard them referred to as the halogens. Commonly in your exams, they might appear as the halogens, and it's really important for you to know this definition. So typical properties, they're just a typical non-metal. They have low melting points. A lot of them are a gas at room temperature and boiling points. And their boiling and melting points increase down a group. So fluorine is a gas at room temperature, and down the group you have further down iodine, which is now a solid. Okay. So therefore, the melting and boiling points have increased. They're also poor conductors of heat and electricity. And molecules are made up in pairs, joined by covalent bonds. So because they're in group 7, we know that they have 7 electrons in their outer shell, right? But how many electrons do we want it to have? So we want it to have 8 electrons. Brilliant, exactly. So how does it do this? It does it through covalent bonds. So if we take fluorine for our first example, we can draw on the 7 electrons that it begins with. Okay, so then if another fluorine comes, oops, that's quite far. Another fluorine comes, it can share one of its electrons with this electron, like we do in covalent bonds. So one of its electrons is shared, and the rest are just dotted around. So now, if we count up the electrons in just this individual fluorine, we're now really happy because we have 8, which is a stable configuration. And if we count up the electrons in the other fluorine, that's also 8 electrons in its outer shell. So both of these are now happy as they're the stable noble gas configurations. Yeah, so that's why your halogens are always in pairs. Always come in pairs. No, but not. Okay, so these are. So there's a quick question, would that be a double covalent bond? No, so this is a single covalent bond. Double covalent bonds are like with carbon dioxide. No, we'll go for oxygen. Double covalent bonds, they have 4 electrons shared. So in oxygen, you have 4 electrons in this middle, as each oxygen just has 6. Oops. Can you count them now? If you count up the electrons of this oxygen, it has 8. And if you count up the electrons of the other oxygen, it also has 8. But a double bond, it has 4 electrons shared in the middle. Good question. Okay, so if people want to quickly write that down, and I'll just quickly look through the questions. So you don't need to know which group is more reactive. You just need to know that group 1 is really reactive, and then that's, yeah, you don't really know which was more reactive. You just know that group 1 is very reactive. Why do they share? So the fluorine atoms, they share because on their own they just have 7 outer electrons, but together they can have 8 outer electrons when they form this covalent bond. So yeah, group 7, they do get more reactive up the group. Okay, let's move on to the next. Yeah, so an element of group 1 can react with group 7. That's a very common reaction because obviously group 1 wants to lose an electron and group 7 wants to gain an electron. So this topic is on group 1 and group 7 atom elements. Okay, let's carry on with reactions of halogens. Okay, so electronic structure determines the way they react with other elements. It has 7 electrons in its outermost, and it needs to gain just 1 more to make a stable structure. That's how it works. So when it's in its element form, it's got that covalent bond and it's sharing electrons, so that's how it's gained 1 electron. But it's very commonly it's very common to ionic bonding as well. So commonly, if we say took sodium and chlorine, draw their outer shells. So that one's got 7, sodium's got 1 in its outer shell. Very commonly, the sodium, it wants to lose its 1 electron. So its 1 electron moves over to the chlorine. The chlorine has a negative charge once it gains this electron. Let's say that one's green. And the sodium now has a positive charge because it has lost an electron. Okay, so next page. So some of you may have done this reaction at school, hopefully some of you have. Displacement reactions. This is a test to see which halogen is more reactive. So the elements are more reactive up. So the reactivity decreases down group 7. It's opposite to group 1. Group 1, reactivity increases down the group. Group 7, the reactivity decreases down the group. Yeah, brilliant. Whoever said that group 7 is more reactive at the top and explained it, that's correct. We're going to get to that now. Outermost means, so if we say take lithium as our atom, we have 2 inner electrons, and then one outermost electron. So the outermost electron is whatever is in the outer shell, the last shell. Okay, so have you guys met displaced reactions? Hopefully you have. So we use these to check the order of reactivity. The more reactive halogens will displace a less reactive halogen. So let's see if this appears in the next one. Okay, let's talk through it. So if, say, we had sodium chloride. And sodium chloride, and we're going to react it with fluorine, so F2. If fluorine is more reactive, it's going to displace this and it's going to form sodium fluoride. If it's less reactive, it's not going to displace it and there's going to be no reaction, okay? So because we've said the reactivity of group 7 decreases down the group, and fluorine is above chlorine in the periodic table. Can we see what fluorine is? So look, fluorine is above chlorine. So therefore, chlorine is less reactive than fluorine. So do we think chlorine, that fluorine will displace this chlorine or not? Do you think it will displace it or not? Yeah, it will. Brilliant. Everyone who's saying yes, perfect. So now it's going to go to form sodium fluoride and chlorine. Okay. Obviously, this isn't balanced. We need a 2 in front of here and 2 in front of here to make sure these ones are balanced. But yeah, so this is a test. Once you add this fluorine to this, if it displaces it, we know that fluorine is more reactive. Okay, so that's something to know. Look at the questions. So are the elements more reactive going down or up in every group? This is not, so the only trends you need to know are group 1 and group 7. You don't need to remember the other groups. And group 1, they're more reactive going down the group. Group 7, they're less reactive going down the group. So they're opposites. Okay, now this is linked to our displacement reactions. So the color of the solution is due to the less reactive pair of halogens. So look, these are some colors I think you do have to remember. So if, say, we had potassium iodide and we added bromine to it. So will the bromine displace the iodine? Yes or no? What do people think? Yeah, brilliant, because bromine is higher up than iodine, so it's more reactive. So then we're going to get potassium bromide and iodine on its own. Once again, we're going to balance it to here, to here. Okay, so now we would have started with what color solution? We would have started with the solution of Br2. So we would have started with a yellow solution. And what solution would we go to? The solution, the color of solution of iodine, which we know is darker red/brown. So the color change we see is yellow. So let's say red. So you can say that bromine is either red or brown. So to red. And therefore, this is tested. From here, we know bromine is more reactive than iodine. So that is how these displacement reactions work. Does that make sense? Yeah, fluorine is colorless. Can we move up the screen? Okay, here you go. Or at least you don't need to know the color of fluorine. If you were to take chemistry for A levels, you need to know the other groups. You probably learn a lot more about the other groups, yes, but that will be all taught when you get to A levels. So when you're balancing an equation, the number in front does not ever change the substance. So if you put a 2 in front of here, you're not changing the substance. That's just saying you've got 2 KIs. You've got 2 of these compounds. But if you say put, so what it means is that you've got KI, imagine, well, this is quite bad. bad example because it's an ionic bond. So each individual one looks like this. Okay, but say the way that you would change the composition is by adding a little 2 here. What that now is telling you is that you have this composition, K, I, with another I. So can you see the compositions have changed? When you put a big 2 in front of it, what you're saying is that you've got 2 KIs. When you put a little 2 here, what you're saying is that you have this new compound which doesn't exist. Okay, does that answer your question? Brilliant, okay. Let's carry on then. So yeah, here was our example, like we said. Oh, so this is actually slightly different. So now, what colour are we going to start with at firstly? Let's go back to page 14. So we're going to start with a pale green. And what colour would it go to if bromine is, if chlorine is more reactive? So pale green. Brilliant. So it's going to go from pale green to yellow because chlorine is more reactive. So we've reformed bromine, which has a colour of yellow. Well done to everyone who came up with that answer. Great. Okay, let me just quickly check. So now let's talk about why we see these trends. The colours are in the textbook. That's just what the colours of these elements are. So if you searched it up, it should come up with the same. But these are the ones that I found from the textbook. Okay, so the trend in group 1. So down the groups, number of shells occupied by electrons increases. So therefore the atoms are large down the group. And the outer electrons, they are further away from the nucleus, and so there is less of an attractive force between the two. Therefore, that is why atoms lose their electrons more easily down the group. So if we say take lithium, for example, and compare it to, say, sodium. So lithium has 3 electrons, sodium has 11. So yeah, can we see, look how much further away this electron is from the nucleus compared to, say, this electron from the nucleus. And obviously, the nucleus has what kind of charge? We learned from the first lesson that the nucleus has a positive charge, and the electrons, they have a negative charge. So therefore, there is a strong attraction between the nucleus and this electron. This attraction, however, decreases the further away you go from the nucleus. And that's why it is much easier to lose an electron down the group than it is right at the top where lithium is. And that's why the reactivity increases, because the way that the group 1 metals react is through losing an electron. Yeah, those are like your key points to note. So if you remember these key points, I'll put it up for like 10 seconds. And then if you don't manage to take down the notes, this is recorded and it is sent to your parents. So don't worry, you can re-listen to it and get all these down. Okay. On to 17. So yeah, what we said. So because the alkaline metals, they lose electrons down, so they lose electrons to react. And down the group, it's much easier to lose these electrons because there's weaker attraction between the nucleus and the electron. And that's why the reactivity increases down the group. So now another topic, another thing to remember here about is the shielding effect. So have you guys met the shielding effect in school? What the shielding effect is? No. Okay, so this is part of the topics. The shielding effect means that here we have 2 electrons inside before this electron, right? So because these have negative charges, they shield this positive charge from this outer electron, which means that this outer electron, it feels less of the positive charge at the nucleus. Okay, so this is just a way that the electron the electrostatic attraction between the nucleus and the electron are reduced. So then obviously, the further away we go from the nucleus, the more of this shielding there is, because there are more electrons in between the outer electron and the nucleus, as you can see. So as it gets further, this shielding increases. So there's less attraction between the electron and the nucleus. Okay. Does that make sense? Okay, so that's what shielding does. So what happens with group 7? So it's quite good to note that group 7 and group 1 react in opposite ways. They don't have the same trends. They actually have opposite trends, but they're explained in the same way. So as we know, the reactivity of group 7, what is the shielding effect? You don't really need to know a definition. What the shielding effect means is that the nuclear charge is like cancelled out. Yeah, you don't need to know a shielding effect definition. It just means that this electron feels the nuclear charge less. So it sees less of the nuclear charge because it's shielded by these electrons. So reactivity decreases down group 7 because the size of the atom shielding nuclear charge need to be considered. So atoms in group 7, the way they react, they are looking to gain an electron. But down the shell, down the group, the shell is further away, and so there's less attraction with the nucleus. So if we say take fluorine, for example. We know it's got 9 electrons, 2 electrons in its shell, and then 7 electrons in its outer shell. And it is looking to gain an electron. Yeah? So we're just going to show sodium's outer electron. So yeah, we got that. So what fluorine needs to do is it needs to attract this electron. It needs to attract this negative charge, pull it over for it to fill its for it to react and for it to get this stable configuration of 8. So because this outer shell isn't too far away from the nucleus, and look, we only got 1 shell in front, so therefore there's not much shielding. There is a strong attraction between this nucleus and this electron. So that's why fluorine is the most reactive, because there's the strongest attraction and it pulls it in fastest. Okay. So then what else? So if we say think about chlorine, oh, actually, let's just change this diagram. So we're going to change this to chlorine. What happens with chlorine? It's got, let's go back to 4. It's got 17 electrons. So therefore, it's got an extra shell in between. So can you see it's become an even bigger molecule? So now it's even further the place where the electron is going to go to. So the attraction between the nucleus and this electron that's being pulled in is even weaker. And that's why your reaction decreases down the group. So because this atom is becoming larger, so therefore the attraction decreases. Also, there's more shielding, which means that these outer electrons, they feel less of the nuclear charge. And so therefore, it's harder to attract and gain this extra electron, and that's why the reactivity decreases. Yeah, so look, atoms gain an electron in the outermost shell, small shell, but down the group, the shell is further away and there's less attraction with the nucleus. We'll go over the shielding a bit more at the end. Okay, so now it's harder to attract and gain an extra incoming electron, down the group. Okay, because down the group, there's weaker attraction between the outer electron and the nucleus because you're further away. There's also more shielding, which also reduces these electrostatic attractions. So although some of you may argue down the group, you're going to have more protons in the nucleus, which means there's going to be a higher nuclear charge down the group. But this is outweighed by the effect of increased distance, so a larger atomic size, and this electron shielding. So when you're thinking about the reactivity and how fast and how reactive it will be, you need to think about the attraction with the electron and the nucleus. Okay. Yeah, so here we're reiterating it. So electrostatic attraction depends on the distance between the outermost electrons and the nucleus, the number of occupied inner shells of electrons, which provide the shielding effect, and the size of the positive charge on the nucleus, the nuclear charge. So down the group, there is an increased nuclear charge that is outweighed by more shielding and larger atom size. So electrons are easier to lose going down a group, and that's why down group 1 we see an increase in reactivity, and it's harder for electrons to be gained down the group. That's why for group 7 we see a decrease in reactivity. Okay, so these are the explanations. It's all to do with the attraction between the outer electron and the nucleus. Hopefully that makes sense. Let me just quickly look through the questions. Okay, so apparently, do people want me to go over the shielding thing again? The shielding concept. Yes. There will be a Kahoot. I think it's coming after this. Okay, so how shielding works is if you think about so let's take lithium. So lithium has a proton number of 3. So a proton number of 3 means 3 protons and what? 3 electrons, as we learned from lesson 1. Okay, so we'll draw in our electrons. One electron and then one that's on the outside. Okay, so what we say is that these inner electrons, they shield the nuclear charge. So here we have a 3+ charge, say. So we've got a positive charge in the middle. But these electrons, they shield our charge. So now we can think that this outer electron only sees maybe 1+, because you can sort of think of that these negative charges, they cancel out with this positive charge. So it doesn't see very much, does it? Because of the shielding. So when we increase, so if we go up to sodium, is that any clearer? So the pull on the outer electrons is less because they are further away from the nucleus and because of the shielding. Both of these work together to reduce the pull on the outer electrons. Okay, so if we look at sodium, sodium we know has, I think it's 11, yeah, it's 11 electrons. Well, 11 protons, 11 electrons, because the proton number is 11. So now we're going to have those 2 in this front, then we're going to have another 8, and then we're going to have our last one on the outside. So once again, all of these electrons, they are hiding this positive charge from this outer electron. Yeah, so this means that this outer electron sees less of the positive charge, okay? And therefore, whenever there's less positive charge, there's less attraction between this electron and the nucleus, okay? So it's both, and also not only does it see less of the charge, it's also further away from the nucleus, which also reduces the attraction. If the inner electrons cancel out the outer electron. Sorry, I don't really understand that question. So sorry, this was just an explanation. This was just trying to show that these electrons, they have negative charges that shield this positive charge, because you can think of them, say, cancelling out with this one. But no, otherwise it doesn't have an overall plus charge because there's also this other electron in the outer shell. Yeah, this is all examples. Yeah, we can do that. So you won't get a question about the shielding effect. What you might be asked, we'll see in a bit, is explain the trend down group 1. So why is group 1 more reactive down the group? So what you need to say is that group 1 is more reactive because there is less attraction between the outer electron and the nucleus. And then you need to be able to explain why there is less attraction between the outer electron and the nucleus. So in this case, obviously sodium, you can see that the outer electron is much further away from the nucleus than it is, say, in lithium. So you say, well, the outer electrons is much further from the nucleus, which reduces the electrostatic attraction between the two, which makes it easier to lose. Also, sodium has more electron shielding than lithium, which also reduces the attraction between the nucleus and the electrons. Does that make sense? So you need to just apply this. You won't be asked, what is the shielding effect? You just need to know that the shielding effect reduces the attraction. So the more shells you have in between the nucleus and the outer electron, the less attraction you feel. Okay? Does that make sense? There is a Kahoot, so let's go on to the Kahoot then. Yep. Actually, I need to be able to go on it. Okay, there we go. Let's start the Kahoot then. So I'll give you guys, we'll have a minute for everyone to log on. If people don't have phones or don't have access to the online platform, please just write down your answers and then you can see what the answers are at the end. And yeah, we'll go over the colours formed at the end of displacement reactions after we finish the Kahoot. We'll have some time. Yeah, brilliant. So the more shells there are, the greater the shielding force. Perfect. And that's why there's less attraction between the nucleus and the outer electrons. Very good understanding. Oh, sorry, I didn't press it. Can you guys see the code then? We'll have a minute. So until it gets to 44. Can everyone see the code? Okay, well, I think we're going to start it now. People still coming in? Okay, we'll give it another few seconds. Okay, gonna begin. If you've not been able to log in, just write down your answers on another piece of paper. Okay. So down group 1, the reactivity increases, decreases, or stays the same. Well done. Okay, so we know that the reactivity increases because down group 1, we are losing electrons, right? And the further away from the nucleus that we are, the less attraction, so therefore the easier it is to lose an electron. Okay, well done to you all. This one. True or false? Is this the correct order? So is it getting less reactive from chlorine to bromine to fluorine? Okay, brilliant. Well done to everyone who put false. So the reactivity is decreasing from chlorine to bromine because that is going down the group. But whereas fluorine is actually at the front of both chlorine and bromine. So down the group 7, we go fluorine, chlorine, bromine. Therefore, fluorine is the most reactive. And so that order is not correct. Well done to you all. Getting close. So what's the most reactive halogen? That was kind of, if you think back to the previous slide, might have been slightly given away back there. Brilliant to everyone, okay? So the most reactive halogen is at the top of group 7, and in this case it is fluorine, because we know that the reactivity decreases down the group. Oh, we've had a change. Well done to you all. Okay, so does this displacement reaction occur or not? This is also linked to the previous question. Yeah, well done to everyone who put true. So what matters is fluorine more reactive than chlorine? If fluorine is more reactive than chlorine, then it will be displaced and form this salt. So as we know, fluorine is at the top of the group 7, therefore it's the most reactive halogen, and so the displacement reaction does occur. And it is true. Okay. Ooh, we're having a big change. Be able to keep changing. So last question, guys. What is the correct equation for the reaction of potassium with water? So what did we form? Okay. Oh, this one's quite an even split. This one was slightly a bit of a trick question, as balancing was also involved. But if we think about it, right, the green and the orange are completely, and the yellow are completely incorrect because we haven't formed our hydrogen. So whenever you react group bond metals with water, you always form hydrogen. So therefore, it is not going to be yellow or green. And also green's incorrect because look, it's gone from from potassium to sodium, which is of course not correct. And then also, if we look at the red one, it's not balanced. We have 2 oxygens on the right. We have 4 oxygens on the left. No, sorry, 2 oxygens on the left, so that's fine. We've got 4 hydrogens, however, on the left, and only 2 hydrogens, and only 3 hydrogens. Oh no, that's fine. The potassium's incorrect. So we've got 2 potassiums on the right, and the potassium is incorrect on the left. Okay, so let's see who won. So well done to Boris Johnson 2.0. Brilliant, great effort. Okay, so now any questions? So we've got some past paper questions ready, but let's get back to this one. But we can go through some questions quickly. So one of the questions is how do we determine the color formed at the end of a displacement reaction? Okay, so let's go to our displacement reactions here. So okay, this is a good example, right? Firstly, with a displacement reaction, if this one is more reactive than this one, it will be displaced. So if we had Br2, so what a displacement reaction is, this, so these are salts, okay? So no, the potassium chloride does not have a colour. It is said to be colourless. So this is a salt. In displacement reaction, if this goes into the salt, that means it has been displaced. That's what displacement reaction is. So if we had Br2 plus 2KCl2, so Cl2, so will bromine displace the chlorine? No, because bromine is less reactive than the chlorine. Therefore, all we're going to form is exactly the same on the other side. There will be no chemical reaction. There will be no colour change. Okay? But up here in this example, chlorine is more reactive than bromine. So therefore, it's going to displace bromine, which means it's going to go to form this salt. Okay? So if we start with this chlorine, we know that its colour is pale green. Once it's been displaced, it's going to form this colourless salt, and we're going to form this bromine, which is going to have a yellow colour. So that's how you determine the colour change. At the end of the displacement reaction, the colour is whatever is as a halogen. So the salt, it doesn't have a colour, but whatever the halogen is by itself, that is your colour of the end solution. Does that make more sense to Joe? Yeah? Okay, brilliant, well done. So that's how you judge that. So you need to memorize these colour changes. Where are they? They're on the previous slide. So these are quite easy to find. So if you just memorize them, they might come up in your questions. Do people have any other questions before we move on to the past paper questions? So you don't need to know the colour change. You need to know the colours of these different halogens off by heart. So you need to know that chlorine is a pale green colour, bromine is a yellow colour, and iodine is a dark red colour. So if you say get a question, you get a question like this: will the bromine displace the iodine? Who thinks? What do people think? Yes, brilliant. So what colour are we starting as? So what will be the colour on the left-hand side? So what was the colour of bromine? We need to remember back the colour of bromine. So the colour of bromine, we were told, was yellow. Perfect. So it's going to start off with this colour, the colour of the halogen. And then what are we going to form? Do you want to write that down? We're going to form sodium bromide. Yeah. And then we're also going to have this I2. So what colour will be on the right-hand side then? What colour will be at the end? Brilliant. Red. Perfect. Or brown. Either colour works. So our colour change we see is from yellow to red. Okay. And then obviously we need to balance it. Yeah, so it's just those three halogens that you need to remember the colours for. So what it means for an element to displace, it means that this bromine, so wait, where's that equation? So it means that this bromine is now as a salt. So we start off with the iodine in a compound with a sodium, right? But the iodine is displaced from this compound by the bromine. So now bromine is chemically bonded to the sodium. That's what it means. So firstly, we start off with the sodium and the iodine chemically bonded, and we end up with the sodium and the bromine chemically bonded. So we can see that bromine has displaced this iodine in the chemical bond. Does that make sense what a displacement reaction is? So the colour on the right is red because here we've been told that iodine is a red or brown colour. Okay. Yeah. Does that make sense? Dun, dun, dun. So bromine is a yellow colour. Yeah, so that's why we start with, okay, so the colour is determined by the halogen. You need to look at which is just a halogen. So whatever's bonded to, say, the metal, that is colourless. So the only thing that determines the colour is the color of these halogens. That's why, although this bromine's on the right-hand side, the color is red and not yellow. Yeah, so the color is always the halogen by itself. Brilliant. Okay, let's go on to the questions then. Okay. So which group are alkaline metals? So if you want to put that stuff in the chat. Yeah, brilliant. Group 1. How does the electron structure of the group 1 elements give their characteristic properties? So in group 1, how many electrons are in the outer shell? Yeah, brilliant. So that's why they have the characteristic properties, because they have one electron in their outer shell. They want to lose just the one. Okay. So then how are group 1 metals stored and why? Yeah, brilliant. Perfect, because they're super reactive and we don't want them reacting with the oxygen. Well done. Everyone's got that? Perfect. Great. Okay, so next, complete these different equations. Can we remember them? So sodium with water, what did it form? So we know they form their hydroxides, right? Yeah, brilliant. And H2. Perfect. Okay. So what about with the halogens? Sorry, these have messed up the numbers a bit. They're meant to be little they're meant to be little twos. So if we react sodium with chlorine, we're going to get sodium chloride. Yeah, brilliant. Exactly. And what happens with sodium and oxygen? Can we remember what the product will be? Yeah, so it's just going to be sodium oxide. So Na2O. Exactly. And to balance it, we would put 2 here, 4 here. Okay. So the next one is just the same. Yeah, sodium chloride is a salt. It's a salt you eat every day. Okay, so I won't do this one because that one's what we just did. Okay, so complete this word equation. So chlorine is more reactive than bromine. So what's missing? Yeah, brilliant. So bromine, exactly. Exactly right. So next, why does iodine not react with sodium bromide solution? So if we had I2 plus NaBr, are we going to see any color change? Yeah, brilliant. So the color is going to remain as red because that's the color of iodine. Exactly. You're not going to see any color change because iodine is less reactive than bromine and bromine is not displaced. Brilliant. Well done. So this one's a bit of a long question. So use the information in the box to help you answer these questions. What evidence is there that sodium has a low melting point? So let's read the box. A piece of sodium was cut easily into smaller pieces with a knife. Sodium was added to some water in a trough. The sodium floated, melted quickly to give a silvery ball, moved on the surface of the water or fizz. So which evidence is it the sodium has a low melting point? Yeah, perfect. The second one, exactly. Great. What evidence is it that sodium is soft? Yeah. So it can be cut. Floated is not to do with it being soft. Floated is to do with its density. The fact has a very low density. So the fact that it can be, the fact that it was cut with a knife is why it's very soft. Okay. So then a gas will produce, what's for the last one? Brilliant, fizz, exactly. Great. Great input. How do we know that two elements combined make a new bond? So that's just a reaction to remember. Sodium and chloride make sodium chloride. Usually if you're given an equation, they will have a reaction. That's what they're looking for, some sort of reaction. Otherwise, you don't need to have that equation, do we? Okay. Okay, so I think that's all we have time for today. So if we wrap it up here, I'll see you tomorrow, 5 o'clock again, and we're going to be doing transition metals and some more practice questions. Have a lovely evening. Bye.